Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now. Arnav, today's topic is too much fun. It's too good, huh? It literally dictates how our lives work, bro.
Yeah, I agree, but chill, you need to take a moment and just chill.
Okay. Moment taken.
Great.
So, what we're going to be talking about today is present in all of our devices. From even the most dabba of the Nokia 3310s.
3310s.
Arey yaar, eh.
Yeah, so from the Dabba Nokia 3310s like your phone,
Yeah.
to the oldest radios to the fanciest TVs.
An ordinary smartphone has 100 million of them, and a laptop has more than 1 billion of them. Can you guess what it is?
Of course, it's a transistor. Electronics on top.
Yeah. So, like I was saying, the transistor is in virtually every electronic device we use. Phones, and even radios. But who even uses radios at this point, though?
Only Dadajis like you.
Please, okay, whatever. I listen to only my Zenith Model 5S220 Cube radio like twice a day. Oh, what a beauty, I must tell you.
Yeah, the Zenith model, blah, 5, blah, blah, whatever is definitely great. But just so you know, it doesn't even have transistors, which is our topic for today, kind of. But it does use 5 vacuum tubes, and it was made in 1938. But I'll give it credit because it was used before transistor was even invented. So
Yeah, fair enough. The charm of those classic tube radios is just unbeatable, yaar.
yeah, okay, fine, Dadaji. Now let's just see how modern radios like my Sony ICF radio actually work with all their millions of transistors.
Okay.
So the basic principle is actually incredibly simple. It just works like any other switch. Like, for example, if you're at home and you're turning on the light to watch YouTube or turning off the lights to sleep or whatever, it switches on and off the stuff that it's controlling.
And a transistor specifically controls the flow of electric current. So it can be off and you can call that the zero state. And when it is on, you can call that the one state.
And that's like a convention, but this is basically like computer science binary stuff, like zeros and
Yeah.
ones.
I also see some quantum mechanics brewing here.
Yeah, superposition.
Yeah.
And this is how all our information is now, right now, like in this day and age, stored and processed in zeros and ones, like little bits of electric current. But in this, unlike a switch, the transistor doesn't have any moving parts and doesn't require a human like us to push it.
Yeah, basically it doesn't require any human to control it.
Yeah.
Yeah, and it can also be switched on and off more quickly than any other switch can be flicked on and off.
Yeah.
And most importantly, it is incredibly tiny. I'm talking like nanometer level.
Yeah, and all that is just thanks to the miracle of semiconductors. But I should say actually the science of semiconductors, not actually a miracle.
Thank you, please. The science and miracles do not mix well together. Of course, other than Newton giving up and going to God.
Yeah, if you know, you know, and if you don't, then check episode 7.
Yeah. It has all the good stuff.
Yep.
Anyways, as we were discussing, pure silicon is a semiconductor, which means that it conducts electric current better than insulators, but not as well as other conductors like metals, for example. But metalloids on top, bro.
Yep. So now pure silicon is a semiconductor, as we said. That's because an atom of silicon has 4 electrons in its outermost of valence shell, because those 4 electrons allow it to form bonds with its 4 nearest neighbors.
Nearest neighbor algorithm.
Kinda. It basically forms a tetrahedral crystal.
Okay.
Because of its 4, right? Tetra is 4.
Yeah.
So all these electrons are stuck in bonds, but because of them being stuck, few of them get enough energy to escape their bonds and they don't travel that much through the lattice.
By the way, a lattice is a geometrical arrangement of points or objects over an area or in space. Where that is like the textbook definition. It's basically you can consider it as the arrangement of vertices in a crystal. I think that's more a better way to explain it.
Or the arrangement of simply atoms in a crystal.
Yeah.
So having a small number of mobile charges or moving charges is what makes silicon a semiconductor. Now this won't be very useful without a semiconductor secret weapon. Doping. You've probably heard of doping, and it's like when you inject a foreign substance in order to improve performance.
Doping, you say? That's interesting.
Yeah, it's like exactly like that, except on the atomic level. There are two types of doping called N-type and P-type. So, to make an N-type semiconductor, you just take pure silicon and inject a small amount of an element with 5 valence electrons. So, like, for example, phosphorus. So, like, basically, we're just injecting a small amount of other material, right?
Correct.
So, this is useful because phosphorus is similar to silicon. It's like similar enough that it can fit into the lattice, but with that extra 1 electron because of its valence, like 5 valence electrons, right?
So this means that now the semiconductor has more mobile charges,
Correct.
and so it conducts current better. But in p-type doping, an element with only 3 valence electrons is added to the lattice, like say boron.
Okay.
Now this will create something that we call a hole. It is a place where there should be an electron, but there isn't. But this still increases the conductivity of the silicon because electrons can move into it, right?
Oh, so like both ways, 3 and 5, both up.
Yeah.
So now, although the thing is that electrons are moving, right? We also can talk about the holes moving around, like the boron case.
Yeah.
Because there's a far fewer number of holes.
Correct.
Since the hole is a lack of an electron, it usually acts as a positive charge. And that's why p-type semiconductors are also called p-type, because of the positive.
Correct.
The P stands for positive, literally. So it's positive charges, these holes which are moving around and conducting the current.
Yeah, it's a common misconception that N-type semiconductors are purely negatively charged and P-type semiconductors semiconductors. Okay, I will not butcher this. Semiconductors are purely positively charged. I mean, that's not true. They are both neutral because they have the same number of electrons and protons inside them. The N and P type actually just refer to the sign of the charge that can move within them.
So in N-type, it is negative electrons which can move, and in P-type, it's a positive hole that moves, but they're both neutral. And a transistor is made of both N-type and P-type semiconductors, so like both are required.
Correct.
And a common configuration is basically N on the ends and P in the middle, so like a sandwich kind of thing. So like NPN.
Yeah.
Just like a switch. Basically, a transistor has an electrical contact at each end, the two ends of N types.
Correct.
And these are called the source and the drain.
Yeah, but instead of a mechanical switch, here there is a third electrical contact called the gate, which is insulated from the semiconductor by an oxide layer. And when the transistor is made, the N and P types don't keep to themselves. Electrons actually diffuse from the N type, where there are more of them, into the P type, which just to fill the holes, right? Yeah. And this creates something called the depletion layer.
This is giving like O3 ozone vibes.
Yeah.
And you may ask, like, what is exactly being depleted, right? The answer is that the charges can move, as literally we're talking about mobile charges, right?
Correct.
So the N becomes the P, like N type goes to the P type, and there are no more free electrons in the N type because they've filled the holes in the P type. Now this makes the P type negative thanks to the added electrons.
And this is extremely important because the p-type will now repel any electrons that try to come across from the n-type.
Yeah.
So the depletion layer actually basically acts as a barrier and it prevents the flow of electric current through the transistor.
So like when it's off, the transistor's off, it's like an open switch. It's in the zero state.
Yeah.
To turn it on, you have to apply a small positive voltage to the gate. This attracts the electrons over and it overcomes that repulsion from the depletion.
Yeah.
And it shrinks the depletion layer so electrons can move through and form a conducting channel. So like if it reduces the layer, it's easier to pass through for the electrons.
So wait. Now the transistor is on and it is in the one state.
Yeah.
And this is remarkable. Just by exploiting the properties of a crystal, we've been able to create a switch that doesn't need any moving parts. And it can be turned on and off very quickly with just a small minor voltage. And most importantly, it can be made extremely tiny.
Yeah, I mean, transistors today are like 22 nanometers wide. This is 10 raised to minus 9.
Oh my god.
Which means there are only about 50 atoms across.
Oof.
But to keep up with Moore's law, they're going to have to keep getting smaller. And the Moore's law basically says that every 2 years, the number of transistors on a chip will double. So like...
Come on, man. Even Edward Witten could hypothesize that. It's so basic.
Fair enough. But there's a limit to Moore's law because as the terminals get closer and closer together, the quantum effects will become eventually more significant. Correct. And electrons will actually be able to tunnel from one side to other, quantum tunneling. So you may not be able to make a barrier high enough to stop them from flowing. So Moore's law may not be applicable after a certain point.
Correct. Now, I I think this will be a real problem for the future of transistors, but we'll probably only face that like another 10 years down the line.
Fair.
So until then, like the way we know them, transistors are just gonna keep getting better, and it's just good for us, right?